Hello, I'm Brain Rainey, and welcome to my Choose Your Own Adventure Lab. Students will investigate and model any system that can lead to physics principles being displayed. To model the system, students will use Tracker to trace the motion of the main object in their system. They will also create at least one physics model to predict something observed in their data. Lastly, they will compare their prediction model or models to the experimental model. For my lab, I analyzed the motion of a falling object before and after it bounced off the ground. I then used the experimental data to calculate how much energy was lost after the collision with the ground. This was then compared to a created GlowScript model of a perfectly elastic collision. Fundamental principles. The main fundamental principle for this lab is Newton's second law, which states that the net force is equal to the mass times acceleration. This is why the ball accelerated, as there was a net force acting on the ball, the force of gravity. This also explains why the ball finally stops moving when F net equals 0, and when all the energy is lost. Another fundamental principle used in this lab is the energy principle, which states that the work is equal to the change in energy plus Q. This principle can be used to show the transfer of gravitational potential energy into kinetic energy during the initial fall and how the object eventually comes to rest when all the energy escapes the system. Like I said earlier, when F net equals 0 as well. Now here's my video. I was dropping a baseball from a given height. You can see my tracker motion analysis. Here are my results. On the bottom is the experimental position versus time graph, and the top is the prediction position versus time graph. You can see here the value goes below 0, which is less than ideal. I'll discuss that later in my coding. There was an error. Not necessarily an error, but I just couldn't figure out how to keep it at exactly 0, but I'll talk about that later. That's not super important for the model. The prediction model models an elastic collision, which is why it has the same peak. And you can see here, if I extended it, it has the same exact peak at a little bit over 1.5, which is exactly where I dropped it from. However, due to the difference between the models, the experimental model is clearly not of an elastic collision, but instead of an inelastic collision. And that is because the peak is not at the same height as the initial drop, which means that energy must have been lost during the collision. And this could have been due to the sound that was made when the ball was dropped, but most likely it was due to the fact that it was a collision with the ball and the earth, and that means the earth had moved a little bit due to the collision, but since its mass is so large, it was a very negligible amount. You can't tell by the human eye. Also, it's important to note that it's not a perfectly inelastic collision, because that would mean they would stick together. Here are my data measurements and observations, and you can see by the two photos, these are where the two peaks are at 0.405 meters and 0.144 meters. And by calculating the change in gravitational potential energy between the peaks, we can determine the energy lost in the first and second collisions with the ground. And here are the gravitational potential energies at the initial position and then at the two other peaks. And here are the changes. And you can see the first change in gravitational potential energy is much larger, which means a lot of energy was lost during the first collision, and the second one more was lost, but not nearly as much. And eventually, when the ball stops moving, all of the energy is lost. And here's my model, which those are the force diagrams. The cyan arrow is the force of the contact of the ground, and ideally it would only be at an instant, but due to the coding, it had to last multiple times, whereas the orange arrow is the force of gravity. You can see here the orange line is constant, which means energy is not changing, even when the gravitational potential energy and the kinetic energy are changing as well. And that was because it was a elastic collision in the theoretical model, which means no energy escapes. Here's my coding. First, I changed the initial conditions of the ball's mass, position, and velocity, as you can see up here. I also have the constant values for G, J hat, and the contact force proportionality constant, which I chose to be 10 after trial and error, and that's included in the force of gravity and the force of the ground calculations, which were used for the net force. And then I included the velocity and position update formulas in the iterative process. Now I also included coding for energy to create that energy graph. I included the initial kinetic, gravitational, and total energy formulas, and then I had to set the initials in the iterative process, the while loop, and lastly I included the energy update formulas in the information on the graph on how to make it. All in all, the actual experiment was not an perfectly elastic collision, but instead was inelastic. Like every collision in the world, it's actually like basically impossible for there to be a perfectly elastic collision. We only use that in physics. But yeah, my lab shows that, and I hope you enjoyed.